Now that we've developed the notion of a vector, let's take a minute to step back and look at matrices with a new perspective. So as a first step, recall that we started using vectors as a way to package a bunch of numbers together. Well, if we can package a bunch of numbers together, then what's to say that we can't package other objects together, like vectors? In fact, if you slice it just right, a matrix is nothing more than a package of packages of numbers. That is to say, if an m-dimensional vector is the data of m numbers, then we can adopt the convention that an m by n matrix is simply an n-tuple of m-dimensional vectors. And we express this by writing the columns as the vectors v1, v2, down to vn inside of brackets as a specific shorthand. So here's an example. Suppose we have the three vectors v1, v2, and v3. If we want to create a matrix using these three vectors as the columns, then we can think about that 3 by 3 matrix as an array of three-dimensional arrays. So if we're thinking about these matrices as arrays of arrays, then we can think about the operations that we've defined on regular arrays. So when we had vectors, remember that we defined the sum of two vectors of the same dimension to be the component-wise sum. So for two matrices, we should be able to do the exact same thing, except instead of defining our component-wise sum to be a sum of two numbers, it's a component-wise sum of the columns, which are vectors. So we start out with two matrices, A, whose columns are v1, v2, down to vn, and B, whose columns are w1, w2, down to wn, of the same dimension, meaning that each of the v's is an m-dimensional vector, and each of the w's is also an m-dimensional vector. We define the sum of these two matrices, A plus B, to be the component-wise sum of the columns. So A plus B is also an m by n dimensional matrix, whose first column is v1 plus w1. The second column is v2 plus w2. On down to the nth column is vn plus wn. For example, consider the following 4 by 4 matrices A and B. If we want to add these two matrices together, then we simply add each of the columns as vectors. When we add the first two columns together, we get 1 plus 6, 4 plus 7, 0 plus 12, and 5 plus 11. Next column gives us 3 plus 9, 5 plus 0, 2 plus 4, and 3 plus 0. The next column gives us 8 plus 3, 3 plus 5, 1 plus 3, 1 plus 1. And finally, our fourth column is 2 plus 2, 7 plus 3, 4 plus 1, and 11 plus 1. So our first column is 7, 11, 12, 6. Our second column is 12, 5, 6, 3. Our third column is 11, 8, 4, 1. And our fourth column is 4, 10, 5, 12. So just like for addition of vectors, addition of matrices follows some very similar rules to addition of numbers. We record here each of these properties, and it's a good exercise to sit down and see if you can show that these things are true yourself. So if A, B, and C are all m by n matrices, then 1. Addition is commutative. That means A plus B is equal to B plus A. 2. Associativity. A plus B plus C, in parentheses, is equal to A plus B, in parentheses, plus C. And 3, there is an additive identity. The m by n matrix, which we call 0, with all entries 0, satisfies A plus 0 and 0 plus A are both equal to A. So just like for vectors, where scaling by a real number means multiplying each of the entries component-wise by that single real number, we can scale the entries of a matrix by scaling each of the columns. So when we talked about vectors, we defined scaling by a real number A to be the product AV, which is multiplying each of the components of our vector V by A. For a matrix A, with columns V1, V2, down to Vn, an m by n matrix, and A, any real number, we define A, the number, times A, the matrix, to be the m by n matrix with column 1, AV1, second column AV2, down to the nth column AVN. So suppose we have the 4 by 4 matrix whose columns are 1, 4, 0, 5, 3, 5, 2, 3, 8, 3, 1, 1, and 2, 7, 4, 11. And we want to scale this matrix by 5. To do so, we simply scale each of the columns by 5. So our first column will be 5 times 1, 5 times 4, 5 times 0, 5 times 5. Our second column, 5 times 3, 5 times 5, 5 times 2, 5 times 3. Our third column, 5 times 8, 5 times 3, 5 times 1, 5 times 1. And our fourth column, 5 times 2, 5 times 7, 5 times 4, 5 times 11. So the result is the matrix with columns 5, 20, 0, 25, 15, 25, 10, 15, 40, 15, 5, 5, 10, 35, 20, 55. And again, just like scaling vectors, we have two familiar properties from multiplication of real numbers that transfer to scaling matrices. For A and B, any two m by n matrices, little a and little b, any two real numbers, our first property is distributivity. That says if I add two matrices together, then scale them, that's the same thing as scaling the two matrices, then adding them together. Associativity says if I multiply the two scalars, then scale the matrix, that's the same thing as scaling the matrix by B, then scaling the matrix BA by A. So this is a good exercise to take the fact that scaling is distributive over vector addition and scaling is associative for vectors, and use those two properties to show distributivity and associativity for matrices